So this week we considered the topics of correlation and regression, and I made a point in the lecture that the learning outcomes really, up to 3,432 of them, a very big number, are plot your data. And most important thing is we can fit regression models very easily. We can compute correlation coefficients very easily, but it's so essential to plot your data, it can't be understated. And we will look a little bit at regression and hypothesis tests, but that's really the single biggest take-home point is plot your data. And first, there's a small caveat. When we use the word correlation, as a scientist, you've got to be really careful with terminology. The minute you've got your scientist hat on or your lab coat on, you've got to forget what you think correlation means. In science, it's telling us something about the strength of a linear relationship between two quantitative variables. You hear it used in all sorts of other ways in everyday English, and to be honest, I wish we'd accept that and come up with a different technical word for correlation, but that's not going to happen soon. So just remember, when you're using this in a scientific context, it has a very specific measure, and it's attempting to describe the association between two quantitative variables on a scale that goes from -1 to +1. And the idea is that, as it were, there is an imaginary line that could be drawn. You don't care how steep or how shallow that line, there could be a line drawn, and if it's positive, it's x goes up, y goes up, and if it's negative, x goes up, y goes down, or vice versa. So there could be some kind of line drawn, but it's measuring the scatter of the data around that line. And when you have a correlation of 0, there's so much scatter, you couldn't tell that there's a line there at all even. So it's really about scatter around an imaginary line of some other than being positive or negative. You don't care how steep the line is, it's about the scatter around the line. So that's the idea of the metric. It is possible, you can construct hypothesis tests for correlation. We'll briefly look at one. And the standard test that you might see used is written there in all its Greek jargon. Capital H subscript 0, the null hypothesis. The statement we make for the null hypothesis is that rho, this is the Greek symbol for the letter rho, which is used to denote correlation in the population, the true value of correlation that we're trying to estimate from our sample. And we say that rho equals 0. The population correlation is 0. And the alternative hypothesis, H subscript A or H subscript 1, is that rho is not equal to 0. And the reason I think this has little value is all you're doing is saying correlation is not 0. And there's far more interesting things to know about correlation than it's definitely not 0. Because who cares if you've got a very, very tiny correlation that's not 0? What you want to know is it a big correlation, is it a small correlation? And that's not what the test's telling you. So I don't think they have any value, but partly to practice the logic of tests, we'll have a quick look at this. And you can also get confidence intervals for correlation, which would be much more useful than a hypothesis test, but you very rarely see them used in practice, even now. So mention them briefly, but won't say a huge amount about them. And again, part of the problem is just because you've said, you're making a statement that correlation coefficient might lie in the range, it's still not completely clear what it means in terms of is this practically important or not. And by way of an example, and to illustrate some key scientific points here, I'm going to run with some data we've looked at before, and it comes from the Health Survey for England. So as we've said, this is a very large, very professionally conducted national study on our health, and people are thousands of people are randomly selected, and all manner of material is measured on them. And I'm using the Health Survey for England 2011 teaching data set. The reason it's a teaching data set is not anything particularly to do with it being simpler than the full data set. It's it's a teaching data set because they've gone to more trouble to make sure that individual confidentiality can be respected if we're opening it up to a wider audience. So don't think this is a simpler or more artificial data set just because it's 2011 teaching data set. And there we can see a scatter plot that shows us the relationship between BMI on the x-axis and systolic blood pressure on the y-axis. And we had a great time in the lecture going over this, had some great comments and criticisms, and trying to encourage you as scientists to make those criticisms. You don't have to know, certainly when it comes to statistics, you don't have to know all the answers. But the more confident you become in making the criticisms and observations, the better. And some people noticed that there looked like there might be some positive correlation. Didn't particularly look like a straight line, but it did look as if higher body mass index was associated with higher systolic blood pressure. But there's a lot of spread, and what some people noticed is the points in that plot are just too dense to know what's going on in the middle of the plot. And the current stage of your careers, that's the kind of critical observation we're encouraging you to make. And I went on in the lecture just to say, well, here's a few things you could do about this if we had to. And one is I've taken a random sample of the plots, of the points. So I've taken 20% of the data so that it's not too dense. And that alarmed some people because I've thrown away 80% of the data. But it's also what we do whenever we randomly sample things. So it might give us an impression, it should still reflect what's going on, but we can get over the density that way. And another thing I looked at very briefly was the idea of a two-dimensional density plot. And here, the lighter the colour, the more dense points we have, the more individuals lie in that little box in terms of BMI and blood pressure. And as I said, we could spend 10 or 15 minutes making sure we all understand exactly what this plot is showing you. And it does deal with the density and reflects what's going on in the data. But again, science is about communication. And the minute you step up to using a plot like that, again, you have limitations on how many people you can communicate with. So, it looks like we're kind of looking at a hill with contour lines and the blue lines, the top of the hill where we have the greatest density. But what's interesting is that the impression we get here is we're not seeing an imaginary straight line particularly. If anything, it's crescent shape. It looks like there's it just goes from a slope to a straight line as we get slightly higher. So assuming a correlation measure that assumes we can describe these data by a single number is going to be limited. And again, that's the scientific point. The serious scientific point is asking the questions, criticising the information you're given, constructively criticising. Anyway, I want to reiterate this. Don't panic at this stage of your career. We're not saying you should know about all these kinds of plots and the many more which I didn't use, and the even more that I don't know exist that I could have used. At this stage of your career, we're encouraging you to build up your constructive criticism. So what matters is that you hold your hands up and say, look, that plot 1 was overcrowded, and that's the skill we want. Critical thinking. Plot 1 is too dense. I can't really see what's going on. And it's also valid as you go through your career. You have to communicate. And if figure 3, that coloured in density plot, was not something you think you could explain to a general audience, there's a problem with that plot. So, as it happens, whatever stage of your career dealing with those data, there is a challenge there. And what matters at the moment, though, is your critical thinking. For any data you're given at the moment, the standard method should be good enough. But it is still good practice to build up your critical thinking, your constructive criticism as we go through this. And went on to look a little bit more at at what it means to reduce a scatter plot to a correlation coefficient. And we did a couple of exercises on Mentimeter, and here is a plot of completely fictitious, made-up data. There's only 11 observations, and the data's been simulated to have different correlation coefficients. So top left, we're looking at a correlation of 0.8, and bottom right, we're looking at a correlation of 0.9, and it shows you there is still a lot of scatter around some imaginary straight line, even when you have quite high correlations. So if you look at set 2, which is top right, it does have a correlation of 0.2, but it's very difficult to say we can see a strong relationship there. And perhaps more surprisingly, set 3, it has a correlation of minus 0.6, but again, it's not obvious from just looking at the numbers that there's any kind of relationship there. So a kind of visual calibration, again, it's just to reinforce the point you should look at your data. Either you have to have a comprehensive catalogue in your head of what these different correlation coefficients might look like, or you always look at your data. And we also did this other exercise on Mentimeter. These are very famous data made up by Anscombe, and the point is they all have exactly the same correlation coefficient. It's all 0.8, and yet what you're meant to imagine, if somebody says the data has a correlation of 0.8, you're meant to imagine that the data look like set 1. That's when the correlation coefficient is a meaningful summary. And yet for sets 2, 3 and 4, everyday actual real things could have happened that make the correlation coefficient a false summary of what's in the data. So in set 2, there's a perfect relationship between x and y. It's just not lying on a straight line. And if you use correlation coefficient, 0.8 doesn't tell you just how strong that relationship is, because it can't cope with the curve. And again, asked a brilliant question during the lecture, aren't there methods we could use to deal with that? And the answer is yes, there are, but you've got to see it first. So again, at your stage of the career, what we're asking is that you just see that and say, oh, hang on, correlation coefficient isn't going to summarize that data well enough. So here's my scatter plot. And quite what you do next isn't a problem for you at the moment. What is a problem is being able to do the scatter plot and say, hey, I don't like the look of that. Set 3, what's gone wrong is we have a perfect straight line with the exception of 1 point. And that is exactly the kind of thing that can happen in your laboratory calibration curves. That you have data that lie up very well on a straight line. That's what should happen in a calibration exercise. But you or somebody has just done something wrong with one of the processes that gave you the answer to one of the points. And again, if you summarize that in a single correlation coefficient, or as we'll go on to look at regression equations, without having first checked out the data, you've got the relationship all wrong. So again, the important thing is look at your data. And in set 4, there is absolutely no relationship between the variables. You can see for 10 of the data points, it doesn't x is always the same, yet there's completely different values of y. And the reason we think there's a correlation is because of that leverage point that's way off in the top right, that lets you calculate a correlation coefficient of 0.8, even though that's nonsense. And again, that's the sort of thing that happens. You rarely see a completely straight vertical line like that, but what you do get is a blob of nothingness and one weird leverage point that makes you think there's a relationship between variables. And again, the point is look at your data first. And then of course it gets even worse, because you can have situations where the correlation coefficient does accurately describe what's happening in the data, but it's still meaningless. And you can follow a link there. Tyler Vigeland has a website on spurious correlations, and he looks at things like the number of people who've died because they got wrapped up in their bed sheets is correlated with the number of films that Nicolas Cage released in a given year. It's completely meaningless, but it just happens that you get these completely spurious correlation. It's If you look at it enough data, it's going to happen. And again, your scientific knowledge and your ability to design good experiments, that's how science gets knowledge that's robust to this kind of stuff, because you design experiments. You don't just go hunting for bits of data and see if they're correlated. You will conduct designed experiments where you randomly allocate different things to different treatments. And that's how you avoid all of these problems. So it's the design that matters. Anyway, having done those warnings about the limitations of the correlation coefficient, it's easy enough to calculate. I've calculated one in R there. There's a command called core. I supply the X variable and the Y variable, and because I'm using a data set that's got this problem that only respondents who had a nurse visit got their blood pressure measured, so I've said just use complete data. And it goes off and tells me that correlation coefficient is estimated at 0.39. Now, two things to say there. That sounds actually like quite a high correlation for a natural phenomenon in observational data. So that for all the caveats about what the scatter plot says might be going on, and that not being entirely appropriate for a simple linear correlation coefficient, that still sounds quite high. However, if you were working in your lab constructing a calibration curve and found out the correlation for your work, that would sound worryingly low. So it's context specific what it means. But and as I said also earlier, it is possible to do hypothesis tests. And again, there's a command in R. Instead of core, you type cor.test, core.test, and it goes off and performs a hypothesis test for you. And as you can see, the p-value is tiny. It's basically 0 to compute a round-off error. So you reject the null hypothesis. Whatever the correlation coefficient is in the population between BMI and systolic blood pressure, it's not 0. So you reject the null hypothesis. And you can also see that procedure, that R function, gives you a correlation a confidence interval. So it estimates a 95% confidence interval 0.37 to 0.42. And you know, knowing all the caveats and cautions there are around interpreting correlation coefficients as a single number summary of a complex relationship between two variables, you've got to decide whether 0.37 to 0.42 is practically important. And that's everything we really said about the correlation coefficient. So I will stop this video here, and we'll have a second video that looks at regression.